Welcome back to the Big Data Analytics and Cloud Data Mining course. We're on lecture 11, and this is part 2 of the lecture. This part will consider data mining and deep learning for healthcare. But first, let's just recap what we talked about in part 1. So mostly part 1 was about applications of association rule mining. And we talked about this application in retail, where association rules are algorithms. Association rule mining is an algorithm to extract relevant information from transaction data, especially transaction data that looks a lot like shopping carts. And we talked about two specific algorithms, in this case, a priori and FP growth, which adapt to the data they're used on, but also require the person applying them to know about the data that they're using and about the algorithms themselves and about the resources that they have. That way they can choose the proper algorithm for the proper application, and also to take advantage to the max of the resources that they have available. And this data mining approach of association rule mining is, we talked about it in the end, is also applicable for the healthcare system or for other applications in different fields. It depends only on how you look at that field and your own perception of your field. The more you understand your field, the more you can apply different problems or different solutions from other different fields into this one. So with that in mind, now we're going to talk about deep learning for healthcare. And I think you've already mentioned, you've already gone through some applications of deep learning and image processing in previous sections of this course. We'll just recap a bit and then go into the details of some of the work I'm doing in this case. But mostly towards the end, we'll talk about a very useful application of a standard way of dealing with machine learning problems, because that would make life a whole lot easier when you have a kind of like a questionnaire or a flow diagram that tells you exactly how to deal with every data mining or machine learning problem that you have. So this process is called the CRISP-DM process, but we'll talk about it later. Mostly right now, we're going to talk about the deep learning and cloud data mining. So I think you've seen one of these in many places on the internet, the CAPTCHA system or the reCAPTCHA system. So you think this is just a method for you to prove that you are a human and not a machine. And this is a very good approach to proving identity, because as we all know, the internet has that problem where there's a lot of bots. But on the other hand, this is a very good resource for Google for their development of image recognition software. These images, in this case, are asking the user to detect where the crosswalk is. But at some point, you realize that sometimes you get pictures that ask you to recognize where the fire hydrants are, where the curbside is, if there's a fire truck, if there are trees, if there is a car in the picture, a biker, a motorcycle. So these pictures change depending on the problem that is currently being discussed in the media. And that's something that you have to be very careful when you're looking at news. This is something that you have, like, you extract this information as you read between the lines. What it took me a very long to realize is that this is Google's way of getting labeled data. They have all of these pictures from everywhere when they get their cars on the street that take pictures, the street view. They have all of these images. These are images taken by humans. They are not labeled images except by location. But when you click on these images, you are telling the algorithm that, okay, label this image as having a crosswalk. And then they would have an algorithm that goes, a deep learning algorithm in this case, that goes through all of these images that are labeled as crosswalks and tries to extract from them the information that is in common. And we'll get to that in a second, but before we get to how this algorithm or this machine learning algorithm is doing this kind of recognition, let's talk about deep learning itself. So in this case, this is an application of data mining on the cloud. And on the other hand, we have here a kind of representation of what a deep learning algorithm does. It's an algorithm that looks at images and tries to extract information, highlight parts, and forget about other parts in order to make predictions about the content of the images. In this case, we're talking about images, but it's also something that can be applied to different applications. It could be applied to voice recognition, it could be applied to text recognition, and it could be applied for time series analysis, which is one of the applications that I'm working on. But we'll get to that later. Now, before jumping ahead, let's talk about how it happens. So shallow learning is a system where you train a small network. In this case, it's called a classification network, to give an answer based on some input. These applications are usually networks that have 1, 2, or 3 layers. They are not very deep, and that's where the name deep learning comes from, where the first layer takes the inputs, the second layer does some calculation, and the third layer does the output. This calculation happening in the middle might be complicated or not, but it doesn't matter much in terms of how accurate the network is. It just provides some way of leveraging one result over the other. In this case, the features are hand designed, in this case, which is where the data analysis part comes in, where the person training the network, in this case, let's still call it a network. In this case, the person training the network has to, by hand, clean up the data thoroughly in order, and they have to be very well curated for this specific problem. And you can see where this is a problem when you have a large amount of data, and also when you have a very accurate network. You cannot by hand go through every image and try to improve it. And also, you cannot train every single layer or every single neuron from this layer in order to improve the results. You have to have a network that does this on its own. So this is where the concept of deep learning comes in, where the network automatically tries to improve itself in order to improve parts of itself in order to improve the total of itself. And in this case, it still requires some data analysis when you're providing the data to it, but it doesn't require the very hands-on approach of data cleaning or data manipulation. Also, the network itself has some forward and back propagation algorithms within it that try to nudge it towards a direction. The only thing that you, as a data analyst or data scientist, have to provide is input data that is relatively clean or well distributed, and the expected outputs. The network will do everything in between and try to make A equal to B. The problem here is, of course, that you're making a black box, and that's a major problem right now because everyone is shifting towards the whole idea of explainable AI. But as a basic application of deep learning, this was a breakthrough. This technology was a breakthrough. So you can see here an example of how it works, where The first layer takes an input, and the second layer tries to extract low-level features, in this case, the eyes, the mouth, the lines that cut off one part from the other. The second layer, a second layer, or maybe like 5 layers deeper, would slowly constitute these low-level features into a mid-level feature, the whole eye with the eyebrows, instead of just looking at the point of the pupil. Maybe the nose with the holes and the angles around it, the nostrils, and then as you get closer to the classifier at the end, it shows more high-level features, the whole face. It's looking at the whole face at this point. And this is where you start getting closer to actually giving an actual answer. That's why it's called a simple classifier, where it classifies things into A, B, C, or D, for example. Man, woman, dog, cat, maybe there were some, the most basic example is mostly about digit recognition, which is 1, 2, 3, 4, 5, 6, 7, 8, and 9. And there is an online application of this, if you search for it, where you can see exactly how the algorithm is working. But we'll get into the details of that later. But first, if you look at this, it might not be exactly clear what's happening. But if we go back to this image here, imagine this is the picture of the face here. The first layers would be looking at individual lines. The second layer, or further layers, would be looking at the collection of these lines, how they interact together. And then further layers would be the collection of lines, until in the end, we have some classification happen. It gets more complex by making things more abstract. And here we mentioned that lecture 6 talks a bit more thoroughly about the deep learning theory and method. But in our case, we are going to talk mostly about convolutional neural networks, because that's one of the applications I'm working on right now. So the network presented before, and where we talked about the way it's abstracting images, this is the basic concept of how a convolutional network works. A convolutional neural network, a CNN for short, applies convolution to layers of the image in order to abstract these layers, abstract the information contained within, applies a combination of pooling and convolution layers in order to provide a description of what is in the picture at the end. In our case, one of the networks that we worked on is the COVIDNet, which got a lot of publicity during the pandemic. It was developed by Wang et al., and they had to do a lot of work in terms of not just developing the network, but also curating the data that would be used to train this network. So specifically for COVIDNet, but more generally for respiratory conditions that push people in so far that they have to go to ICUs, sometimes it's very difficult to diagnose these problems. And these problems, usually, the quicker they are diagnosed, the more likely that the patient will have a positive outcome. And since it's the goal of medicine is to improve outcomes for patients, faster diagnosis means more survival. Especially when it happened to COVID-19, when it came to COVID-19, the faster we are at detecting it, the better it is for the patient. Maybe we can just immediately start working on the how to mitigate the condition, instead of just trying to know what the condition is. So if you have an algorithm that does this diagnosis quickly, efficiently, even if it gives some false positives, but at least it's better to be safe than sorry in that case. So can we train a neural network that looks at images of chest x-rays and extract from them enough information to be able to make a diagnosis? We saw that doctors themselves are able, by eye, to look at these images and be able to recognize that this patient is healthy, this patient has some problems with their lungs, this patient definitely has COVID-19, because it was already established that COVID-19 had a specific fingerprint in the chest x-rays, where patients exhibited something called the ground glass aspect inside the lungs. And this is also the same aspect that shows in one of the other conditions that I have, meaning that they are related. One of the other conditions that I'm working on, sorry, I don't have it, thankfully. So one of the other conditions I'm working on has the same appearance in chest x-rays. And the thing is that it's not that COVID-19 is causing this, it's that COVID-19 is causing a reaction in the lungs that causes that other condition that I'm working on. So we saw that my original project and the COVID-19 project were kind of merging on some level, and we thought we would apply it for the data that we have, or like use the knowledge that we have in order to improve the COVID net neural network. So this COVID net neural network we're going to talk about exactly how it is, but mostly the whole idea of it is to improve diagnosis by building on the available data that was collected by scientists, because also it became clear that all of these hospitals that have sick patients that have COVID-19 had to come together, bring this information together and share data in order to help improve the diagnosis for this condition, because it's a global problem. So the questions to ask in this case are, do we have enough images for this kind of task? Of course, we have a history of images of healthy lungs versus pneumonia, but do we have enough images for COVID-19? If we do have enough images, do we have legal access to them? In their case, for Wang et al., they were able to compile some of the openly available COVID-19 images into a data set that was called the COVID-X data set, which is openly available for research purposes. It's on Kaggle if you ever have the urge to work on image data. But also, they did a great thing, which is compiling this data set from very many different sources. One of the main problems with healthcare is that the open data that is available sometimes is very biased by being all sourced from one hospital. That was the one hospital that was okay with sharing the data online. That means that data, since it's open, a lot of people use it, meaning that all of the people working on training neural networks are introducing this kind of bias in their neural networks. So having a data set that's collected from different parts, has different types of images, and is able to show different types of data helps improve the robustness of the neural networks being trained on it. Finally, we need to look at the computing resources that we have. In our case, thankfully, we have access to supercomputers, but a hospital in a third world country might not have that kind of access. How can they still improve their diagnosis using this kind of information? So with that in mind, we think about the whole idea of the CRISP-DM process, which I mentioned before, which is the standard for data mining. The CRISP-DM in this case means the cross-industry standard method for data mining and machine learning. We'll also talk about where it's sourced, but here we have the reference to it. You can go also into the references section of this presentation if you want to read more about it. But mostly it's an application, it's a loop, and it forces the data scientist or the data analyst to understand what the problem they have is, to understand what data they have, and then based on this new understanding, go back to try to understand the problem that they have, maybe find a better way of solving it. And based on that, look at the data again, see what they can remove. And then do this on several iterations in order to distill their information into something that is more relevant, something that is more applicable, more within the bounds of reason. We do, as scientists, we do have some things that are unreasonable, and this helps us rein it in. So with this kind of with this kind of approach in mind, let's talk about CNNs and residual networks. And based on that whole idea of like knowing what resources we have and knowing what data we have, let's see how we can improve that. So I think you've seen in lectures 6 and 7 how CNNs and residual networks work, but I'll just give a short refresher about that. So like we mentioned, CNNs use several layers of convolution, pooling, convolution, pooling in order to extract information about how the pixels in an image deal with each other within an image and how they are relevant one to another in order to help classify the contents of this image. And they are very accurate. This is how your phone can detect that your face is in an image. If you own an iPhone, or actually any Google phone right now as well, you can search through your own images. And this doesn't mean that your images have been uploaded to the cloud, just offline images. The algorithm is able to highlight things within images. You search for cat, it finds all of the pictures in your albums that have cats in them. So convolutional neural networks are well adapted to learning from image data, but you don't really need to build your own convolutional neural network. In this case, there are several networks that you can just buy them or use them off the shelf. They are open source. The ResNet 50 is one of these networks, which is available out of the box in the Keras package for Python. It's also available for PyTorch for people who are used to working with Torch. ResNet 50 is the winner of the IAAS VRC image classification task for 2015. This task is how well and how accurately and how quickly a network can be trained to detect the contents of images. And ResNet 50 blew everyone out of the competition because it was so efficient at detecting the contents. And this network builds on the whole concept of residual layers, where one of the main problems that convolutional neural networks deal with is the exploding gradient problem, where at some point in the convolution layers, one of the neurons might just either go to 0 or go to infinity in terms of how important it is. And by doing that, it either completely cancels out the whole region that it's looking on, making the network impossible to train, or completely blows out everyone around it, like a short circuit, and it limits the ability of the network to learn anything. So at some point you reach this kind of like threshold where you cannot learn more with your network. So by doing this whole idea of residual layers, you can have a normal access through all of your layers, but also give it a shortcut. In case this layer is not useful anymore, it adds the previous layer to the current output in order, and you can see it here, where this shortcut allows it to do some addition of the original input with the output from this layer. By doing that, you kind of allow the network to skip parts where if you're at the point where the network is just like kind of slowly slowing down, this allows it to jump ahead of it and maybe give it another push to learn more. The specific ResNet 50 was trained on 1,000 classes from the ImageNet database. in this case. They are for animals, objects, and shape detection. But the makers of COVIDNet built on that in order to just detect 3 classes. Their 3 classes are COVID-19, non-COVID pneumonia, and healthy patient. So by building on this residual idea, their network is more capable of looking at these images and learning from them without running into the exploding gradient problem or disappearing gradient problem. This network, as I mentioned before, is trained on the COVID-X dataset, which they compiled themselves, which is great for them. And also the network is available for researchers online to download and use. It's a bit complicated to use, but because you have to work with earlier versions of TensorFlow, which is the machine learning and deep learning platform for Python, or one of them at least. In our case, we thought about applying it on a larger scale. So the data set from COVIDNet is open source and it's openly available. But what if we have a hospital in the middle of nowhere that has their own data that they cannot share outside? And then they give us access to this data in order to improve their algorithm. Can we do it with the data that they have? So we tried to apply it to this data that was given to us by eHealthline, which is one of the project partners that we're working with. We apply COVIDNet first with the COVID-X dataset that we have, just to highlight that it works properly. We look at the data that we have from eHealthline and try to, first of all, clean it because it might not be exactly 100% top-notch data. At the same time, we try to see how different that data is from COVID-X, because if the network is trained on COVID-X, then it's trained to a specific standard. It will not perform well on eHealthline. And as expected, it did not. The images that we had from that partner were reduced in size and in quality in order to fit on their available storage. So does COVIDNet work well with reduced quality data? The answer is no. So it was clear that we had to retrain it. This is the step where you do some data understanding, but also some problem understanding. In any case, the network itself has several versions available online, and there is a version that deals with smaller, lower quality images. Based on that, we used the data available to retrain the network, and we retrained the network on this eHealthline data, and then ran it and tried to perform a validation step again. The same validation step we did where we tried to run it as is on the eHealthline data, this time after training. And by doing that, we saw a clear improvement in the results. The network was better able to detect COVID-19 in these images. It wasn't that good at detecting pneumonia images, mostly because the data set that we have is a bit smaller and there aren't enough images to be able to form a proper diagnosis. But still, this highlights that there is some improvement that can happen. We can, of course, play with parameters, and this was the next step that we plan to work on, currently working on right now, as we speak, by the way. Automated hyperparameter tuning is the next step of our research, where we apply an algorithm developed under the Ray framework. This algorithm allows the network to actually trains the network on several iterations using several parameters, changing them, nudging them one step up, one step down, to be able to improve the outcomes of the network, and also killing the networks that are not improving. So by doing that, the algorithm in this case is able to detect the best performing model and also the best performing combination of hyperparameters. With that in mind, we move on to one of the major aspects of one of the major advances in deep learning, which is the whole idea of transfer learning. You see, COVIDNet itself was initially trained on ImageNet, which we talked about here. It's trained just like ResNet 50 on the images from the ImageNet database, which is a large collection of images of dogs, cats, horses, objects, just random daily objects. In order to make the best, to extract from that information the network's ability to detect shapes in images. And based on that, it was retrained on the images from COVID-X. So this whole idea of using a pre-trained network and then giving it a new problem to solve based on the knowledge that it already has is called transfer learning. Transfer learning. So the original network is taken as is. Some layers are frozen where they won't learn anymore, and some layers are unfrozen where they might be retrained. And then you remove the final classification layer that was built in the network and replace it with your own classification layer. This classification layer has the information that you require, and then you retrain the whole network on these new classes that you're trying to detect. Sometimes it could be just, is this COVID-19 or not? Sometimes it could be the same 3 classes, but in a different approach. So this whole idea of applying transfer learning to something that's already available is one of the major advances in this, because besides the fact that you don't have to build your own network, you're also not limited on the performance of the original network either. You can have a network that's openly available and also improve its performance based on the data that you have, but specifically for the data that you have. And this is also another aspect of problem understanding and data understanding. And so by doing this, we were able, as I mentioned, the results in this case that we had for the data that we have, and also the hyperparameter tuning, we have applied transfer learning to COVIDNet itself, and we have some results. We're waiting for further results in order to be able to publish them. But at the same time, this is how science happened. This is like the slow step-by-step iteration for the improvement of a algorithm that exists in order to make something that solves future problems or current problems. And at the same time, the data that we have from eHealthline is not limited to just COVID-19, pneumonia, and healthy patients. Their data also has patients that have collapsed lungs, patients that have trauma, where like the images show trauma, images show things being introduced into the lungs, or like infiltrates where tissue is breaking down inside the lungs and it causes a reduction in breathing. All of these conditions are highlighted in their images in a labeled data set. So we can apply this to the classification layer at the end of COVIDNet. And instead of just being at 3 classes, we can apply it to 10, 15 classes of different conditions from lungs of ICU patients. And that way, we can build a network that is portable. It doesn't need to be retrained because it's trained on their data. So they are more likely to collect similar data to the one that they have. They just need to apply it to this network. And they run it as is. And so they would have a diagnostic tool. It's of course not going to be a tool that's going to replace the medical staff, but it's something that gives the medical staff a nudge like, hey, based on previous data that you have, this patient might have this. Maybe give them a bit more attention. And that's how you improve healthcare in this case, because because it's been clear that medical staff have something called decision fatigue, where after a certain time, they cannot make adjusted decisions based on the situation. This helps. This is a very good thing to reduce the number of alarms they have to deal with, and instead just highlight ones that need attention. Another example that I'm working on is for ARDS diagnosis. ARDS is a condition where the lungs of the patient slowly stop working. It's a drastic reduction in the performance of respiration in these patients. And it's very difficult to diagnose because there are a lot of things that cause. So COVID-19 causes ARDS in this case. For us to be able to detect this condition, we developed this neural network, which is a very basic convolutional network of 5 layers. 4 convolution layers and 1 classification layer at the end. This model is just dealing with time series data and snapshot data from medical signals, but not at images. So you can see here, this is an application of convolution, but on linear data, not on image data. And this came about after an understanding of the problem and the data that we have. The problem with ARDS is that it's difficult to diagnose, and it's very, as they say, heterogeneous. And at the same time, it's very difficult to treat because every different ICU has a different way of treating it. Morris and I usually describe it as being like, let's just like adjust this and reduce that. Maybe that works. If it works, great. If it doesn't, then we can just nudge it later. But at the same time, it follows the whole idea of like the earlier it is diagnosed, the better it is for the patient in terms of outcomes. So by building this network, we hope to be able to train an algorithm that can easily ring an alarm bell when the patient is heading in the direction, or at least predict that the patient will head in that direction within a specific time. And in order to be able to extract this kind of information of when this happens, or like, does this patient go in that direction, we build on data that we already have, and we build on a simulator that was developed by John Hardman and his colleagues at the University of Nottingham. Their model was built in MATLAB, which, as you know, is not really fun to work with, and also not very open. So instead of using that model, we train a model on the outputs from that model, and that model that we train is more portable, more open, and it doesn't break the whole idea of data intellectual property. So running a model in MATLAB is quite slow. If you've never experienced it, I hope you never do. But running a machine learning model, in this case, training it might take some time, but running it as is just for inference is very easy. The only problem we have is that the data might not be consistent or might not be enough. And the data that we had was definitely not enough. Here we have a snapshot of what the data looks like. And through some data analysis, we were able to highlight that this data follows a normal distribution. And based on that normal distribution, we were able to generate our own data that mimics all of this data that we have. And by mimicking the data, we did some form of data augmentation, which we'll talk about later. But also by doing this, we kind of cheated the system where we understood the data that we have. And in order to solve the problem that we have, we tried to provide more data, because training a model on a small amount of data is just going to give you a very bad model. Now, the whole idea of training a neural network sounds like a very easy thing to do, but for any of you who have tried this before, I don't know if any have, this can just grow incredibly large. In this case, we're looking at a section of the ResNet 50, where we're at the 5th convolutional block. So each block has about 3 or 4 convolutional layers and a residual layer. So after 5 convolutional blocks and then a classification layer here, we see that the network has 25 million trainable parameters. If it takes a microsecond for each of these neurons to training a network for 10 epochs might take 5 hours if you have a basic processor. And that's where the That's where the cloud resources come into play. Sometimes you might be part of a research institution and have access to supercomputers. In my case, that's what I have. But sometimes you don't. Sometimes you need to train this network based on the available resources. And if these resources are not available, then you have to depend on cloud providers. Google Cloud offers Google Colab, where you can have access to GPU. Amazon Web Services and Microsoft Azure, as you've already seen, I guess, provides access to Apache and some cloud computing resources where you can do this training without having to cripple your computer. Even if your institute has access to a large-ish computer, it's still sometimes a financial and it's still a sound decision to use these available resources, even if they are paid. But it helps. It might make you use it for a short time, instead of using your available resources for a very long time. That way, it opens up your resources for other research applications. So training on these resources makes network train a lot faster, a lot more efficiently. It introduces the whole idea of maybe having to store the data on not very secure platforms, but that's where anonymizing and cleaning your data makes it kind of like unreadable by anyone who isn't you. So you also have to understand how to work with the data and also what to do with the data. Data augmentation that I mentioned before is the whole process of fixing the problem of not having enough data. And in this case, we're talking about images, but it also can be done with numerical data, as I mentioned in this case here, the ability to generate similar data to the one that we already have. Image recognition in this case requires a lot of images, obviously, and augmentation is one of the shortcuts around this whole problem, where you are students in Iceland, you know where this picture was taken. We take the original images and we apply some zooming in, some rotation, some panning. It moves the image from one side to another. It introduces some noise into the images, but the main part of the image that we need to detect is still there. It's just shifted in a way that it makes the network a bit more robust. And it doesn't break some of the major rules of data, where I mean, if you don't have enough data, get more images, yeah, but where am I going to get them from? And also, you cannot train over the same images all the time. That makes your network really good at detecting the same image, and that's it. That doesn't help with prediction. So by generating your own images, you kind of improve your network's ability to find the thing that you're looking for in different conditions. Changed colors, still can see it. If you look at an image that is highlighted in red, you can still detect the cat in the image, for example, or the spider, or whatever triggers some emotion in you. You do that because your brain is working really hard at detecting objects in the images before it even looks at the colors in the image. Sometimes it bases this detection on the colors, but when in the absence of colors, your brain still can do it. So it does that by constantly being bombarded with images of things, where it extracts information from these things. And we're doing the same thing with the convolutional neural networks that we have. So data augmentation is one of the major solutions for the problem of sparse data. And it doesn't necessarily negatively affect training results. Sometimes it does. But at the same time, it's a shortcut in order to have a network that works based on the problem that you have. And finally, we get to the whole idea of the CRISP-DM process. So this is the cross-industry standard process for data mining. And I mentioned before that it takes a lot of like problem understanding and data understanding. So you have to constantly be doing this loop in order to know what you're doing, know what you can do, and know what you have to do in order to solve the problem that you have. From there, you move on to the data preparation section where you do the cleaning. Also, you do the development of the model that you have. This is also another loop that you have to go through where you improve the model based on the data that you have and improve the data based on the model that you have. After that, you do some evaluation, and then you go back from your evaluation to the original problem that you have. Did I solve the problem? I didn't. I have to go through all of this all over again. And so your job is to understand what you're doing and to be able to do it in the best way possible. To understand that, you have to understand every single aspect. That includes the data, the software, the hardware, and how well you understand all of these things. So it takes a lot of problem solving in this. And this is also where Occam's razor comes into play. If you don't know it, that means finding the simplest solution to the problem is often the best solution to the problem. Your job is to find that solution. Your job is to find that solution also based on your understanding, based on your experience, and it will only improve with your experience in the field. As you work more with the data, as you work more with networks and algorithms and hardware and software, you start developing this whole concept of being able to solve a problem in a counterintuitive way. But you can no one can give you that knowledge, no one can give you that information. This is something that you will have to do on your own, and you will do it. It just takes a lot of time and experience. So this is mostly what I wanted to work on, but I wanted to talk about, and this is what I'm working on. But I wanted to mention also the whole idea of how learning happens. And in this case, in the beginning, we talked about the fact that association rule mining is an unsupervised learning method. And this is exactly what I'm still working on. The whole idea of like, you prepare an algorithm and it automatically extracts data that you probably don't know you needed from that data that you already have. It extracts information, and that information can become new data in order to solve a new problem or to train a new model or to provide better diagnosis. Supervised learning is another approach in terms of data science. And then there's reinforcement learning, where just constant exposure to things makes the network more able to detect things. Supervised learning is mostly the whole idea of telling the network, this is what you're looking at, and then giving it new data to be able to see if it is able to detect the thing that you told the network about in new images. So technically, you're constantly going to work on something that is a mix between all of these three. Reinforcement learning, maybe not that much, but mostly a combination of these two, supervised learning and unsupervised learning. And the whole idea is to use a set of observations to uncover an underlying process. This is what unsupervised learning works on. But mostly, this is how learning happens in any case. The only reason you're giving this information to a network is because you know that there is something to learn from this. So moving on, besides learning, you slowly through your work kind of start establish connections with other researchers in the fields, get to have their perspective on how they solve their problems. And this leads us into establishing the connections that within the Icelandic community and within the international communities, where we managed to like bring the Icelandic HPC society, also in collaboration with the German data science and computer science and medical field. I'm as I mentioned before, a founding member of the International High Performance Computing Society for data for health and health and medicine. And since I'm working in Germany right now with the Jülich Supercomputing Center and the Uniklinik in Aachen, I'm more in cooperation with these experts in the field. And this kind of has given me a lot of experience in terms of like how they solve problems and how I would have solved problems. And this collaboration brings us to one of the main aspects of the field, which is also competition is very helpful. I don't know if you've read in the news, but recently 2 teams have developed 2 kind of antagonistic or maybe competitive approaches to solve the protein folding problem. And if you don't know the protein folding problem, that's a problem that's plagued scientists for more than 100 years, of how proteins kind of fold on top of each other when they're being constructed. These 2 teams managed, one of them is funded by Google and the other one funded by the University of, I forgot which university, I think Stanford. These 2 teams, each of which developed a different approach, both of them using deep learning, but both of them converging on the whole idea of like deep learning can be used to train, it can be used to build a model that is able to detect this kind of protein structure. And also this whole idea is that several layers, several modules of this model, in order, because it's something that happens one step at a time, the model itself should also be able to mimic this approach of looking at the first part, small sections, second part, larger section, and the third part, the whole thing. So the 2 models, each of which performs differently and does different different kind of detection, but together they might be a very good tool to solve the whole protein folding problem. And with that, I think I'll link to these at the end in the bibliography, and you can read up on them if you're interested. But with that, I get to the end of my presentation. I thank you all for being here and for listening, and I hope to answer any of your questions. You can reach me by email or over LinkedIn, and I'll just go through the bibliography just quickly here. Thank you for thank you for being here, and thank you for being interested in this. And I hope to be able to answer any of your questions if you ever have them. Thank you very much.
All right. Yeah, thank you very much, Chadi. Very interesting lecture, very interesting insights. Indeed, Chadi is a 3rd-year PhD, so he had experienced lots of interesting elements of the data analysis, including lots of difficult data sets, if I may say. So please feel free to reach out to him, perhaps also not only about, basically the idea of being a data scientist, maybe also what a PhD entails at the University of Iceland. I think also there, Chadi can tell you a little bit what the life of a PhD means. We will continue with practical lecture 11.1 next time, so see you then.